Hi, in this video we will introduce the notion of critical numbers. These are the points at which a local maximum can happen. So a number C in the domain of the function of a function f is called, so we have a name for that, critical numbers, or a critical number for f, if either, there are two conditions, either f is not differentiable at that point, at that value of x, or it is differentiable but the derivative of that function is equal. This is the definition. Whenever you have a function and you have a point at which the function is not differentiable or the function is differentiable equal to 0, we call that one, those points or those numbers, critical numbers. And well, now actually we can rewrite the Infermos Theorem. The Infermos Theorem says that if f is f has a local max or mean value at C, then C is a critical number for f. So that's just, we put the terminology into the theorem and rewrite it. This is what it says. So this is why critical numbers are important. These are the points or the values of x at which a local max or mean will occur. Okay, so let's do some examples and see how this works. Paste. Okay. Find the critical numbers of given functions. Well, first thing, see that f is differentiable everywhere. Well, because it's polynomial. So as a result, critical numbers of f can only be of a type 2. Well, type 2 is not a good terminology. What I mean is that they will satisfy the second condition. And to find them, we need to find the derivative of the function, which is 6x squared minus 6x minus 36, and set it equal to 0. This gives us 6x minus 3x plus 2 equals to 0. And from there, we have either x is equal to 3 or x is equal to negative 2. So f has two critical numbers. Either x is negative 2 or 3. And well, that's how we find it. Okay, how about this one, f prime at x? So we try to find the derivative first thing. And when you differentiate this guy, well, this is product rule, yeah. So this is the derivative of first one times second one plus the first one itself times the derivative of the second one. And differentiate x to the power, this is as x to the power 1/3, and the derivative would be 1/3 of x to the power negative 2 over 3, 1/3 minus 1, times x plus 1 plus x to the power, let's just write half. Derivative of x plus 1 is just 1. Let's simplify. You see, this guy here goes to the denominator. So here we will have x plus 1 over 3 third root of x squared plus the third root of x. Let's write this a bit more simplified form. If I do simplify this one, this will give us 4x plus 1 over 3 the third root of x squared. Well, there are two things that you can see here. First thing is that f prime is not defined at this point at x equal to 0. You see, in the denominator I cannot plug in 0. Also, you see that we can set f prime of x equal to 0, and this will give us 4x plus 1 over 3 times third root of x squared equals to 0. There is a fraction, then the whole fraction is 0 if and only if the numerator is 0, and that means that x is negative 1 over 4. And while in this example we have both of critical numbers of the both types. So f has two critical numbers, x equal to 0 and x equal to negative 1 over 4. And let's move to the other one. Well, f prime, this is differentiable everywhere, so we have to look for the points which make the derivative 0. So f prime of x is 1 minus 2 sine x. Set it equal to 0, and this gives us sine x is equal to 1 over 2. Well, from here you know that, for example, pi over 6 will have the same, will have a 1 over 2, a sine of pi over 6 is 1 over 2. Well, we can also have a 5 pi over 6, or we can have 2 pi go around and come back, so 2 pi plus pi over 6, or 2 pi plus 5 pi over 6, and so on. Well, in general we have these points, 2 pi n plus pi over 6, or 2 pi n plus 5 pi over 6 for all integer number n. Well, this means what? This means that f has infinitely many critical numbers. These are the numbers we have. Yeah. The last example, well, f of x is this. We find f prime of x, and this will give us what? This is ln of u prime over u, and this is 2x over x squared minus 1. Set it equal to 0. That means that x equal to 0. So if you're in a rush, you say, okay, I found a critical number. There's x equal to 0. This is the critical number. But you have to be careful. Note that f of x is defined for only, it is defined for negative infinity up to 1, negative 1, sorry, and then from 1 to plus infinity. And what does this mean? It means that x equal to 0 is not in the domain of the function. And well, that means that there is no derivative, no point that makes the derivative function 0. So it means that f has no critical number. You have to be careful on these kind of cases, because you see, this is a good practice. Why the domain is only here from negative infinity to negative 1 and plus 1 to plus infinity. And these were the examples. We introduced the critical numbers and we did some examples for critical numbers.